Hi class, today we'll be covering Chapter 4. This is a fairly large chapter where we'll be discussing brain development, sensation and perception, and also motor development. Think of that like physical movement. So your brain is comprised of billions of neurons, these specialized cells that process information and communicate with each other. You can see a picture of neurons at the bottom of your screen. There are just two neurons here. But don't think of these like chains. It's not just one neuron to another, but think of it like a network, that one neuron connects with many other neurons. So they have this distinct structure. Just to point out the dendrites, so these are branches from the neuron that receive information from previous neurons from other cells. The cell nucleus is in the center here, the purple. The entire yellow part is the cell body. This is the axon, and this is the direction of the signal. So it receives a signal from other neurons. Once it gets enough of the signal, it activates, and the signal travels down along the axon, and then is transmitted to subsequent neurons. This axon is kind of a long tube-like structure. It carries electrical signals to other neurons, and it's coated in this fatty substance called myelin, or myelin sheath. And this speeds the transmission of those electrical impulses, and it helps with neurological functioning. You can think of the myelin sheath as kind of like water on a slip and slide. It helps you go faster. All right. Also important, synapse here. So this is where one neuron connects to another neuron. So the electrical signal travels down, and then it causes the release of neurotransmitters, which are chemicals, into the synapse, the space in between these two neurons. And that allows for the transmission of information. Neurogenesis is the term that we use for the formation of the first neurons in prenatal development. Now, neurogenesis primarily occurs during prenatal development before birth. However, it does continue throughout life, but at a much, much slower pace. And instead of thinking that you are going to generate new neurons if you need them, instead you should think of it in that you have pretty much all of the neurons that you're ever going to have. It's a very slow process of creating new neurons, so you should treat them well and make sure that you take care of your brain. Also important, glial cells. These are brain cells that provide structure and nourishment to neurons, and they outnumber neurons about 10 to 1. So your brain goes through two different types of development. The first one is experience expectant, and the second is experience dependent. With experience expectant brain development, your brain depends on experiencing certain basic events and stimuli at key points in time for typical development to happen. So for example, vision. Animals that are blindfolded and prevented from using their visual system in the first few weeks after birth, they'll never acquire normal vision because these connections among neurons that transmit sensory information from the eyes to the visual cortex in the brain just won't even develop. So it needs that stimulation in order to develop those connections. And if you wait too long, you miss that critical period. And even if you expose that animal to visual stimuli in adulthood, it won't be able to perceive that because it hasn't developed the connections from the eyes to the brain. So the brain organization depends on experiencing certain ordinary events in life. So the opportunity to hear language, to see the world, to touch objects, to explore the environment, all of that is necessary for typical brain development. The second role that experience plays in brain development is experience-dependent brain development. So this is growth in the brain, and it's in response to specific learning experiences, and it just depends on what each individual person is exposed to. So experiences like learning to stack blocks or crawl on a slippery wood floor, that's all unique to individual infants, and they influence what particular brain areas and functions are developed and also reinforced. So infancy is a time of major growth in the brain. A newborn's brain is about 25% of adult weight, and it becomes 80% of adult weight by age 2. And at birth, neural networks are very simple. If you look at the right-hand side, I've got a graphic showing this, where a newborn brain has fewer connections, and then as children age, you see many more of these connections amongst the neurons. But also I want you to pay attention to the difference between 9 months and then 2 years, and then as an adult. You'll notice that the 2-year-old stage has lots of connections. So what has happened is synaptogenesis, the creation of many new synapses, or that space in between two neurons and how they communicate. What's happening is transient exuberance. The brain makes many more connections than it actually needs in the first few years of life, and this is in preparation to receive any and all conceivable types of stimulation. And the connections that are used become stronger and more efficient, while the unused ones eventually shrink, they show atrophy, and then they disappear. What's happening is synaptic pruning. This is the loss of unused neural connections. So you see in the graphic showing the adult neural network that there are fewer of those connections, and that's because it's saved the most efficient connections and then cut those connections that are less efficient. So I briefly mentioned myelin before, and let's talk just a little bit more about that. Glial cells produce and then also coat these axons with a fatty myelin sheath. Again, this helps speed up transmission. It's like water on a slip and slide, but the myelin sheath can be damaged by actions that you take, like too much drinking and whatnot. So, and also just kind of are damaged over time with age. So our myelin, you really want to preserve it. It helps with that speedy transmission, but with age, we do see a decrease in that myelin sheath. Lateralization is the process by which our hemispheres are specialized. And you've probably heard this before. The difference between left brain and right brain is probably a bit familiar to you. So the left brain focusing more on logic and language, and the right brain a bit more on art, music, and holistic thinking. So we see that lateralization develop. It begins even before birth, but it's influenced by genes and early experience. And I'd say within about 4 months after birth, you really start to see evidence of some of this lateralization. For example, children display a preference for their left or right hand, but then subsequent activities, so they show a preference and then they use that hand much more often. That makes the hand even more dominant because experience strengthens the hand and neural connections and improves agility. And you can think about, yourself. Are you left-handed or right-handed? We would refer to this as hemispheric dominance. That one hemisphere becomes stronger and more adept. For most people, the left hemisphere dominates, and the left hemisphere controls the right side of the body. So you have a dominant left hemisphere if you are right-handed. There's also the growth of the corpus callosum. This is a set of neural fibers that connects the left and the right hemisphere, and this helps with communication between the two hemispheres and coordinates processing of information. And then last bit here, plasticity. I briefly mentioned this before. Just to reiterate, plasticity is the brain's ability to change and adapt to experience, but then also it has an ability to recover from injury. And a young child's brain reorganizes itself much better in response to injury. So if both a child and an adult get the same exact brain injury, a child will recover more quickly and more fully as compared to an adult because the brain is better able to reorganize itself. In adolescence, puberty triggers neurological developments. It kind of triggers the synaptogenesis, the creation of new synapses. And This is a rapid increase in connections among neurons. It strengthens those connections between brain areas, and it leads to enhanced cognitive functioning and also behavioral control. So think about the difference between children and adolescents and their ability to control their behaviors, like getting out of their seat when they want to do something. Adolescents are better able to suppress those urges. There's an increase in cerebral cortex volume and decreases in gray matter. And this is due to synaptic pruning. It helps to thin and mold the prefrontal cortex and results in more efficient cognition and neural functioning. Myelination leads to that increase in white matter. Remember, myelin is that fatty sheath that is around or coating the axon and helps with the transmission of information. So it speeds up that communication in the brain. And because of that, we see improved performance on measures of working memory, executive function, and also of learning. The dual process model proposes that the limbic system, which is responsible for emotion and rewards, it undergoes a burst of development before the prefrontal cortex does, and the prefrontal cortex is responsible for judgment. So the difference between these periods may account for that typical adolescent behaviors. Teenagers seem to sometimes make poor decisions, very emotional decisions, act out impulsively, and engage in lots of risk-taking behaviors and aggressive behaviors. And this may be because that reward area, but then also that area is also responsible for kind of emotion and feelings. And without the control of the prefrontal cortex, an adolescent is ruled quite a bit more by their emotions and by that risk-taking behavior. So it kind of raises an interesting question of having adolescents, to what extent should they be responsible for the crimes and the behaviors that they carry out? Their brain isn't fully developed, and they're a bit more influenced by these emotions and lack the control that adults do. So it really does provide some evidence for treating adolescents differently and not charging them as adults, because simply their brains are just not quite as well developed. In adulthood, we undergo many predictable changes in our nervous system as we age. We lose the myelin, the coating on the axons that helps with transmission and speed of signals. And this happens especially in the prefrontal cortex, that we lose this myelin. And this is what contributes to a cognitive decline with aging. Brain volume also shrinks, and this is due to dendrites contracting and becoming lost, a decrease in synapses, and also a loss of glial cells. However, even though we go through these age-related declines in terms of the brain and cells within the brain, adults are able to compensate for these losses. And we've observed that older adults' brain compensate for cognitive declines by showing more brain activity and using different brain areas in problem solving. And they also show this cognitive reserve, an ability to adapt, to be flexible, to use problem-solving strategies. This is a type of plasticity that's cultivated throughout life from experience and environmental factors. And then also, just to note, I've mentioned this before, neurogenesis, the creation of new neurons, it continues throughout life, but it slows down considerably. Moving on to motor development and tracking motor development across the lifespan. The first movements that infants make are called reflexes. These are involuntary, so it's done automatically by the body. Automatic responses to various stimuli, such as touch or light or sound. And adults have some reflexes too. You may be familiar with the tapping of the knee when you're at the doctor's office and it makes your lower leg kick out just a little bit. Or another one is a puff of air. If someone blows air towards your eye, you automatically blink. You don't stop and think about blinking. It just automatically happens. So infants have a number of reflexes, and these are their earliest ways to adapt. Several are necessary for eating. So for example, the automatic sucking reflex. If you put a finger or a pacifier into a baby's mouth, they automatically suck on it. And of course, this helps them get food from a nipple and is important for survival. Additionally, there is Let's see, the rooting reflex helps with feeding. This is when you brush the cheek of a baby, they turn toward that stimulus. So this would help with feeding as well, because it means that they turn their head toward the nipple in order to get food. So they orient their heads to receive feeding. Let's see, there are a couple others. I've got a video here, so let's see, hopefully it'll work for us. So 9 reflexes of a baby. The first one is blinking. The stimulus is a flash of light or a puff of air, and the reaction is closing both eyes. This never disappears, it's permanent. 2 is the Babinski reflex. This one's pretty cute. So the stimulus is just touching the foot. Brush it lightly at the bottom, and the reaction is to stretch the toe and pull the foot inward. This disappears at about 9 months to a year. Number 3 is the Moro reflex. The stimulus is being suddenly dropped. Of course, you don't actually drop the baby. And the reaction, the baby is shocked, arches his back, flaps his hands, and this disappears at 3 to 4 months. Stimulus again, suddenly dropped, and hands and feet flap out and then close quickly. So it's kind of like trying to grab onto something. Think about a primate baby holding onto its mother when it's almost dropped. Next one is rooting. The stimulus is a slap cheek or mouth that is lightly touched, and the reaction is to open his mouth and start to suck. So he turns his head toward it. This disappears at about 3 to 4 months. There he is, turns his head toward the stimulus. Five is the stepping reflex. So this is showing a stepping reaction. The stimulus, the baby is lifted above the ground surface and the feet touch the ground, and the reaction is he moves his legs like going on a walk. This disappears at 3 to 4 months. 6 is sucking. The stimulus, objects touching the mouth, and the reaction is to automatically suck. This disappears at 3 to 4 months. Seven is grasping. The stimulus, an object touches the palm of his hand, and the reaction is clutching the object. This disappears at 3 to 4 months. Eight is swimming. The stimulus, you put your face or body in the water, and the reaction is making coordinated swimming motions. This disappears at 6 to 7 months. So you'll notice that a baby will automatically make swimming motions, close their mouth and not breathe in the water. And it's also super cute. So there are two main areas of motor development, fine and gross motor development. Gross motor development is controlling large movements of the body, so this helps us get around in our environment. Fine motor development is more like using your hands and your fingers for much more fine and refined movements. Gross motor development continues in a predictable sequence. This is the cephalocaudal progression, beginning with the head and then moving down the body. So you've got the same chart in your book. You can look at it in more detail, but just in general, you'll see that control of the head emerges first. Babies at 2 months being able to lift their head and then hold their head steady when they're held upright. Eventually, development moves down and they're able to kind of push themselves up with their arms and sit without support, so moving down their trunk. And then eventually they gain better control of their lower body and their legs and are able to walk and then to run. Again, fine motor development are these more small movements. Think like tying your shoelaces or handwriting. Again, this chart is in your book, so you can look at it in a little bit more detail. But with fine motor skills, you see that they obviously go from much more simpler, easy tasks like unzipping zippers or putting on clothing or using a spoon. And then eventually at 5 to 6 years, you see kids much better able to control their fine motor movements by tying their own shoes and being able to cut their own food. Just real briefly, I wanted to talk about this emergence of fine motor skills. In particular, the development of grasping. We see different grasps emerge from children, and in a slightly predictable order. So for example, the palmar grasp, when kids grab by the palm of their hand, you see that on the top right picture, that emerges at about 5 to 7 months, where they kind of use their hands like a rake and then grab an object with all of their fingers at once. At around 6 months of age, they're able to transfer objects from one hand to another. And then at 8 months, they're able to use what's called the pincer grasp, like picking up a Cheerio with just the finger and the thumb. By 6 months, they're able to adjust to the properties of an object. So think about how objects are larger or smaller, how they are squishy or firm. Kids are able to change their grasp according to what that object is like. And then by 8 or 9 months, they're able to anticipate the properties and prepare their hand in just a way to fit the size of that object. And around 11 months, they show tool use, like holding a blanket toward them to get a toy. And at this time, hand preference is fairly clear. So there are lots of factors that influence the development of motor skills. For example, just maturation. This plays a strong role in motor development. All around the world, infants display roughly the same sequence of motor milestones. And even with cultural differences in child rearing practices, we see similar patterns of development. And this suggests things like walking are maturationally programmed. Other evidence, identical twins who have more similarities in timing and pace of motor development compared to fraternal twins give more evidence that maturation plays a role in development. Brain development. So as the brain progresses, it allows for the furthering of motor skills. Synaptic pruning contributes to an increase in motor speed. The growth of the cerebellum, this is responsible for balance, coordination, and some aspects of emotion and reasoning. And also the myelination of its connections to the cortex contribute to advances in gross and fine motor skills and speed. So this improves children's ability to inhibit actions as well. Think about the game Simon Says, where you're given commands and the kind of object of the game is when you're not said, when the person doesn't say Simon Says, you're supposed to not do it. So you're supposed to inhibit your kind of natural tendency to carry out and imitate the behavior that you've been doing. Opportunities to practice motor skills. So children need the opportunities to practice. You have to let them go out and be within their environment, and that practice can enhance motor development. And it also contributes to cross-cultural differences in infant motor development because different kids have different environments, and it leads to them practicing different motor skills and refining motor skills depending on what they're exposed to. Also, the child rearing context. Parents from different cultures may choose different techniques to encourage motor development, and therefore some skills are emphasized more than others. And even things like clothing can influence motor development. For example, in the 19th century, many American infants skipped the crawling stage. And this is probably because they were dressed in those long flowing gowns, even boy babies were, and that impeded movement on hands and knees. So it just didn't allow them to practice crawling and go around and crawl, so they just skipped that stage. Just a little bit more about the influence of experience. Experience absolutely benefits motor development. There's this interesting study called the sticky mittens study, where they essentially put Velcro on babies' hands and Velcro on the objects, the toys in their environment. And so this allowed very young babies to manipulate and pick up objects that they wouldn't normally be able to because they don't yet have that hand control. So I've got a video on the upper right-hand side where you can see a baby wearing these sticky mittens. Super cute video. So infants who wore these Velcro sticky mittens, at 3-month-olds, if they wore these mittens, then they grasped and manipulated objects earlier in their environment than the control group. They looked at objects longer, they swatted at them more during visual contact, and they were more likely to mouth objects. So it kind of allowed them to make this connection that they can affect objects and manipulate objects in their environment. 5-month-olds who were trained for 10 minutes a day over a 2-week period showed advances in reaching behavior at the end of 2 weeks. Now, it's important to note that that's only 10 minutes a day. We don't want to put Velcro gloves on babies 24 hours a day, because then they won't actually learn to use their fingers and grasp objects. They'll just rely on the Velcro. So this is just a very short time that they're wearing these gloves. Another interesting example of how experience affects development. Babies who use walkers kind of an excessive amount actually show delayed walking. And the problem may be that they aren't getting the experience of walking outside of the walker. And the walker actually leads them to use unsuccessful strategies. And I'll show you a video of a baby using a walker. And it's kind of funny because he's chasing dogs in this video. Poor little guy. So what you'll notice is that the baby will stand, take a few steps, and then kind of fall down, and then will you know, kind of slide his feet. It's not really natural walking, right? He's taking steps, falling down, taking steps, falling down, and that's because the walker is there to support him. So he's not having to maintain his balance. And also, kids don't have practice moving from one texture to another, like going from carpet over to wood and picking up their leg and stepping over that threshold. They don't have that experience, and instead in a walker, they're just going to power through it. So it doesn't provide a naturalistic experience and can actually delay walking. So in essence, practice makes perfect. It's important to practice motor skills, and babies earlier on had practice with the stepping reflex. So they walked earlier, so they kind of have this idea of moving legs back and forth, and then just engaging in everyday movements, reaching for toys, right? They need those opportunities to explore their environment. Structure isn't necessary. You don't need to stand there and move your child's legs back and forth and back and forth. They'll kind of figure it out on their own, but they need opportunities to learn and to explore. Motor development is an interaction amongst developmental domains, and in the next slide or two we'll be talking about sensation and perception. So the idea that what an infant perceives, what they see, what they feel, and what they understand about the world affects their motivation to engage in motor development, to take action. And this is what leads to development in motor skills over time. It's also a reflection of maturation of the central nervous system, helps with development of motor skills, and also the environment. So the environment provides opportunities in which children get to try out increasingly complex motor skills. So simple motor skills are combined in increasingly complex ways. This permits advances in movement. So for example, skipping, right? Everyone skipped as a child. So skipping, you can think of as being a combination of running plus hopping at the same time. So that's a more complex movement that older children are able to do, but younger children take some time to develop. All motor movement relies on coordination of our senses as well as cognitive abilities to plan and to predict our actions. So again, that interaction amongst various developmental domains. And the social and cultural influences provide a context for our movements and provide motivation and then shape our behaviors. So motor development is a result of the processes of central nervous system maturation, the infant's physical capacities, what they're able to carry out, their strength and their abilities, environmental supports, and then also the infant's desire to explore the world. That curiosity is very important in developing motor skills. Motor skills do improve until early adulthood, reach their peak in about 20s or maybe 30s, and then decline. Physical activity can compensate for some of these normative declines. So again, stay active, use it or you lose it. Balance is particularly important as we age. This is our ability to control our body position in space. And this includes an integration of sensory information and with the awareness of one's body in space and also the surrounding environment. So where is my body and what is going on in my environment and how am I able to maintain my position in space? Our sensory abilities decline in function with age, so it makes balance more difficult. And also with age, balance really taps into our cognitive resources. It takes a lot of attention to balance oneself. And so that's why older adults tend to struggle with balancing quite a bit more so than younger adults. And balance, again, is so important because those falls in older adulthood can lead to breaking of bones, and the bones are more brittle, and that can be quite a shock to the system and perhaps lead to death. Gait, this is the speed at which people walk. It does slow with age, and as muscle strength, bone density, and flexibility decline, that's why people are walking more slowly. But many compensate by taking longer steps. Perception arises from action. Children explore the world around them to learn about it, and through these activities, infants learn to perceive the world. I want you to think about typical infant toys where they have lots of buttons and levers and things that are squishy and things that crunch and whatnot. And so these are really great stimulating toys for infants. It stimulates their curiosity, and then they like to press everything and move everything and see what happens, and that's their exploring of the world. Affordances are the nature, opportunities, and limits of objects, and infants explore their environment, not randomly, but systematically, and they're searching to discover the properties of things around them. And when they find these properties, they learn about objects. It it therefore increases and refines those actions that they can do with those objects as well. Just to add a little bit, because I found this fascinating, affordances are generally the perceived functions and opportunities and limits of objects. For example, buttons, right? Those are a pretty typical idea. Buttons of on an elevator, you press the button and then you learn that the button takes you to the floor that you press. But just so you know, there are all around us false affordances. So this is an apparent affordance that doesn't have any real function, meaning that we perceive a possibility that isn't actually there. And I've heard that the door close button on an elevator is actually a false affordance, that it has to stay open for a certain period of time for individuals who are slower walking or with disabilities in order to get through. And so when you press the door close button, it's not actually doing anything. And I heard the same thing for some crosswalk buttons. It would go through a normal cycle anyways, and the button is just there to make you feel like you're doing something, to make you feel like you have control and like you've been able to take action. Just something to think about next time you're pressing some of those buttons. Then also there are hidden affordances. So there's a possibility for an action, but you can't actually perceive it as the actor. So for example, it might not be apparent from looking at a flip-flop that it could actually be used to open up a beer bottle. But under some flip-flops, there are bottle openers that can be used, just not obviously there. So we'll talk a little bit about sensation and perception. It's important to know the distinction between these two. Sensation is when you detect a stimulus. For example, the light goes into your eyes and then the signal is transmitted to your brain. You are sensing a light or a sound, or you're feeling a touch. So it's some type of a sensation. Perception takes this a bit further. This is your brain making sense of the stimulus and figuring out, what am I feeling, what am I seeing, and also being aware of it. And I just have a funny story about the difference between these two, because sometimes you can be sensing something and perceive that it's something different than it actually is. So I was flying on a plane once, and there was this smell, and it was just a little bit of an odd smell. And my friend sitting next to me leaned over and said, "Oh my goodness, I think someone vomited on the plane." And I thought, oh no, and it all of a sudden turned my stomach, and I couldn't believe it. And I got out anything that had a scent to it in my bag. I think it was lip gloss or something, and I held it up to my nose in order to cover up the awful smell that was turning my stomach. And after about a few minutes of that, we turned around, and the person behind us was simply eating a Caesar salad. So once I recognized what it was, I was like, oh, wait a minute. I love Caesar salads. And once I perceived it as being a Caesar salad and not as being the smell of someone having vomited, my stomach was no longer turning. So just kind of interesting how you can sense something, but then perceive it as being something entirely different. Our brain isn't perfect at it, but it tries to make sense of the world. So let's talk a little bit about research methods in sensation and perception, how we know what children can see and understand and their knowledge of the world. So one method is the visual preference method. So this is simply the length of time looking at different things. We show them at a picture of one thing versus a picture of another thing. First of all, if they look at one thing over another, like a spiral shape versus a face shape, and if they look at the face shape more, this is telling us that infants prefer looking at faces as opposed to looking at other objects. So we do know infant preferences based on time spent looking or orienting toward a particular stimulus. But then also their looking time can indicate to us that they know that something is different. So if I show them a green rattle, and then they get bored of it, and I show them a blue rattle, if they show more attention toward the blue rattle, this is telling me that they can tell the difference between the green rattle and the blue rattle. If they couldn't see the difference between green and blue, then they would be just as bored with the blue one, because they would be perceiving it as exactly the same thing. So that's how we can tell that infants can perceive color and the degree to which they can perceive color, as well as other stimuli, being able to tell the difference between other things. Now, with infant color perception, they can see color at birth. It's not great. This is why having a nursery in pastel color, although kind of traditional, it may be best to do stronger, vibrant colors because they're better able to tell the difference between those colors. So what I was referring to earlier is what's called habituation. And habituation, there we go. Habituation is when a person shows decreased responsiveness after seeing the same stimulus repeatedly. So see the blue rattle. Oh, goodness. See the blue rattle. Oh, see the blue rattle. Start to get bored with it. See the blue rattle. Don't even bother. And I'll show you a video of that in a moment. So habituation is decreased responsiveness, and then dishabituation is recovery of that response, recovery of looking at it after a change in the stimulus. And this shows that they understand that the stimulus has changed. So the one thing that we changed, we know that they can perceive. And it's not just looking, but orienting, so turning toward an object, and also sucking on a pacifier. When infants are interested in something, they suck faster on their pacifier, and we can measure the rate at which they're sucking, and this will tell us their level of interest. So first, on the right-hand side here, I'll show you a quick video. There are no words in this. It's just a video of a young baby who is looking at a rattle and then getting bored of it, and then you can see kind of that habituation process happening. Oh. And here's a video talking a bit more about what babies teach us about perception. And this one's really fascinating because it shows some unique methods of testing infant perception in the research lab.
What was that?
All right, so let's talk a little bit more about age-related changes in our senses and vision, hearing, and other senses. Vision is the least developed sense at birth. If you look at the picture on the right-hand side, you'll see a face as it appears to a newborn on the left, and then to a person with a typical 20/20 vision on the right-hand side. So on the left, it's fairly blurry as opposed to clear. Newborns have vision that's about 20/400, and they tend to reach adult levels fairly quickly, between 6 months and a year. And these large improvements are due to increasing maturation of the structures of the eye and also of the visual cortex in the brain. Newborns prefer to look at patterns and faces. They look at the image on the bottom right-hand side. You can see kind of two paddle shapes. And then on the left-hand side, the circle of the paddle has two squares and a rectangle, and it kind of gives the illusion of two eyes and a mouth. And then on the right-hand side, it's got the exact same shapes, but they're inverted. So instead, it kind of looks like there's a rectangle on the top and then two squares on the bottom. It's less face-like. And children prefer to look at the one on the left that approximates a face as opposed to one on the right that doesn't look as much like a face. And this shows that we have this innate tendency to look at shapes that appear to be like faces. We want to look at faces. We also show an increase in the ability to follow movements with eyes. This is visual tracking. This improves with age over time. Next time you're around a little infant, you can hold an object in front of them and move it from left to right, and you'll see that newborns very, very poorly, almost can't even focus on an object. And then once you get to about 6 months, they're better able to track it and can a bit more smoothly move their eyes back and forth as they track the object. And then, of course, we get even better closer to the time when we, need to write and need to read. That takes a lot more fine focus of our vision. Color vision improves with age. Newborns see color but have trouble distinguishing between color. They need early visual experience with color in order to produce normal color perception. Just a little bit more about what objects see, but then also what they understand about the world. This overlaps a little bit with cognitive development, so we'll be coming back to some of these ideas. At 2 months, they realize that partly covered objects are actually whole behind another object. 5 to 6 months, they understand that objects that are touching are two objects and not simply one object, so they're starting to perceive boundaries between objects. Between 4 and 8 months, they understand object permanence, that an object continues to exist even when it's not currently in their sight. We'll definitely come back to that in the cognitive chapter. And in 6 to 8 months, they understand support and gravity, that an object hanging off a table should fall off, and that's kind of what the figures at the bottom of this slide are showing. The one on the left, the top green box is clearly supported and nothing funny is going on there, but on the right-hand side, the green box looks like it should be tipping off of the table, and they will show surprise at that figure. They will show an understanding that things should be supported and should fall off at least by 6 to 8 months. They'll also show an understanding that ball bearings will travel further when rolled down a longer ramp, and also cup handles should fall off if it's not actually attached to the cup, that they need that support. Depth perception is the ability to perceive the distance of objects from each other and from ourselves. So, for example, the ability to see that, a wall is, 4 feet in front of you, and then a wall even further is 8 feet in front of you. So that's depth, how far away something is from you. Infants can perceive depth from birth, and one way that we have tested infants' perception of depth is with this visual cliff. And the figures on the bottom show that. Essentially, you put the child on a table, and it's got this checker pattern on it, and it's completely covered with a plexiglass even beyond the table. So they can see beneath them. They won't fall because there's a plexiglass there, but then farther down, about 3 feet or so, is the pattern again. So what we're testing is to see that infants can perceive the drop off, the cliff, and therefore are less likely to crawl across it. Now, we do know that even young infants who haven't crawled do show some fear about this cliff. So therefore they do see depth quite at a young age. However, crawling babies readily move to the planks, from the plank side to the shallow side, but not to the deep side. And even if they're coaxed by their mothers, suggesting that they perceive the difference in depth. And the more crawling experience that they have, the more likely they are to refuse to cross to the deep side of the visual cliff. So younger infants are a little bit more coaxed into going across when they get reassurance from their parents, but older infants have more experience with crawling and are less likely to cross over into that visual cliff. Hearing is the most well-developed sense at birth. The capacity to hear develops in the womb, and newborns can hear about as well as adults, and they can discriminate amongst sounds fairly well. Newborns are very attentive to voices. They prefer speech. They even show a preference for their mother's language over others' language because they heard it in the womb. They even show recognition of nursery rhymes or music that they heard while they were in the womb as compared to other music. They can perceive and discriminate nearly all sounds in human languages. And this is very important because an infant, may grow up in any household speaking any language. And so it's important that infants are prepared to speak any language throughout the world. So this next video here is a demonstration of how infants are able to discriminate between all speech sounds early after birth, but then lose this ability around 6, sometimes 9 months. You'll see some varying reports about that. And this video is a little bit old, but I really like this video because it gives an example of phonemes in a different language. Phonemes, this is an idea we'll come back to in the language section. Phonemes are the smallest unit of sound in language. So for example, the word cat can be broken up into three phonemes: k, at, k, at, cat. So that's 3 sounds, 3 phonemes. And languages, although we share many phonemes, not all phonemes are present in every language. So for example, in Spanish, you have the R sound, and in English, we don't have that sound. However, especially if you grew up in Southern California, you've heard words similar to that, so we are better able to perceive those different sounds because we've had exposure to it. In this video, they give an example of 2 phonemes in a bit more of a rare language, and they may sound almost identical to you. So this will give you a bit of experience with trying to perceive the difference between sounds. Quite fascinating there to see how they tested whether or not the infant understood or perceived the differences between those sounds is training the baby to turn her head when the sound changes. Really quite genius there. All right, so moving on to touch. Touch is a critical means of learning about the world, especially through the mouth. You notice the infants in the video that we just watched were, often putting toys in their mouths, and they're learning about the object. What does this taste like? What does this feel like? What is the hardness of it? And so they're investigating about the world. The mouth is the first part of the body to show sensitivity to touch prenatally and remains one of the most sensitive areas to touch after birth. Also important about touch, a caregiver's massage reduces stress in preterm and full-term newborns, and it's also associated with weight gain in newborns. That skin-to-skin contact, it's referred to as kangaroo care, that has a pain-relieving effect for infants. So very important to touch and to hold and have that skin-to-skin contact. And the capacity to feel pain develops before birth. At around the 30th week of gestation, the fetus begins to respond to a stimulus that may be creating a pain feeling. Smell and taste are well developed at birth. Newborns can discriminate between smells and tastes, and they show disgusted facial expressions in response to offensive odors. And newborns can recognize their mother's odor and be calmed by her scent. Infants also show an innate preference for some tastes. They prefer human milk over formula. They prefer sugary substances to salty or bitter substances. And like I talked about before, experiences can modify taste preferences. So the flavors that they were exposed to, via what the mother ate, it goes into her amniotic fluid or into her breast milk. They show preferences for that food later on. So experience shapes preferences. Intermodal perception is when we combine from our various sensory systems to understand the world. So what we see, what we taste. Think about taking the bite of an apple. You're not just perceiving it through one sense, you're hearing the crunch of the apple, you're tasting the sweetness of the apple, you're smelling the apple, right? You put all of these sensory stimuli together in order to really perceive your world as a whole. So infants must learn to coordinate their senses. This is present fairly quickly after birth, that they are sensitive to these intermodal relationships, and they will be surprised or kind of notice when things are off, and when the sound isn't synced to a video. That's something that they could potentially notice and understand, that things should be synced up. You should be hearing things as they hit an object at the same time that you see it hit an object. There are changes to vision in the adult years. Your cornea flattens, the lens loses flexibility, the muscle that permits the lens to change shape weakens, and the lens yellows, the size of the pupil shrinks. We have a loss of rods. These are light receptor cells, as well as cones, color receptive cells. And this leads to declines in night vision and also color discrimination. And then also there's a transparent gel that fills the eyeball called vitreous, and this becomes more opaque with age. Presbyopia is our inability to focus the lens on close objects, also known as farsightedness. And this is caused by the stiffening of the lens eye related to the loss of collagen that contributes to the stiffening of tissues throughout the body. And you can think of this, let's see, an example might be when a person middle-aged or perhaps older goes to a restaurant and they have the menu in front of them, and you'll notice that they may hold the menu farther away as opposed to closer up. So with younger people, they see better closer up, so they're going to bring the menu close. And middle-aged and older, they start to pull that menu farther back because they have less ability to see close objects. So of course, reading glasses can help with that. Cataracts are more common in older age. This is the clouding of the lens, resulting in blurred, foggy vision, and this can lead to blindness if not treated. It's the result of a combination of hereditary and environmental factors associated with oxidative damage, like diabetes or smoking. And last here, macular degeneration. This is a substantial loss of cells in the center of the area of the retina, causing blurring and eventual loss of central vision. So you can see a picture of that in the bottom right-hand side. The center of the vision is impacted. And this is influenced by hereditary and environmental factors as well, like smoking. Hearing. So presbycusis is age-related hearing loss. This is caused by natural cell death. It leads to a deterioration in ear structures, and these structures usually convert sound to neural impulses, but because of cell death, this leads to difficulty with converting what is heard into a perceivable sound. The first to decline is high pitches. So low would be down here, and high sounds like this. So unfortunately, high-pitched sounds are often voices. Voices are more high-pitched than other sounds in our environment, and so this means that a person's ability to hear what is being said around them can be particularly affected. And unfortunately, many people don't get treatment for hearing loss, and this can affect them socially. They may feel more disconnected because of it. Just a bit more about the loss of high-pitched sounds. Which I think is fascinating. And for this, you should, if you can hear, you should turn on your speakers if possible. So this age-related decline in high-pitched sounds happens fairly predictably. So we start seeing a decline even in your 20s and 30s for these extremely high-pitched sounds. And when we're talking about high-pitched, another example would be like if you could, there's a TV that's on in another room, but it's on mute, so you're not actually hearing any sound from it, but you can still hear that, the very high-pitched hum of the device being on. That would be a very high pitch. Now, teenagers have used this a bit to their advantage because they know that they, being much younger, can hear these very high-pitched sounds a lot better than their teachers. So they turn this into a ringtone so that they can hear when their phone is ringing, and their teacher can't hear this particular tone. Now, much hearing loss is preventable. We really do have to protect our ears. When you go to loud concerts, bring earplugs and try to not turn your music up too high, because trust me, you'll regret it later on in life. All right, last bit here, smell and taste. So sensitivity to smell does decline throughout adulthood, but it's not usually noticeable until late in midlife, like 60s or so. And there's a strong link between smell and taste. The declines in your smell ability has implications for taste. And you can probably relate to this if you've ever had a cold and so your nose was stuffy so you couldn't smell anything. Your taste is also affected. That smell adds a lot to the flavor of your food. So as your smell declines, you also are unable to your taste. Older adults are generally less sensitive to taste. And then last, changes in smell and taste are influenced by many factors. So the health of the person can affect smell and taste, chronic disease, the medications that you're taking, and absolutely smoking too can have a negative impact on smell and taste. And people who have been chronic smokers and then quit have really shared quite a bit about the remarkable change in their smell and taste and how food tastes so much better after quitting smoking, which of course is just one of the many benefits. All right, thank you everyone. I hope you enjoyed, and let me know if you have any questions.